We'll proceed to our next speaker. Let me introduce Dr. Ranga Pichumani. You already know him. He's the director of the Concentrating Solar Power Program of the U.S. Department of Energy Sunshot Initiative and the John R. Jones III Professor of Mechanical Engineering at Virginia Tech. In his role at the Department of Energy, Dr. Pichumani oversees a team of technology managers and technical, financial, and support personnel who actively manage the awards in the CSP program's portfolio. At Virginia Tech, Dr. Pichumani directs the Advanced Materials and Technologies Laboratory with research in the areas of energy systems and sciences, materials processing and manufacturing, composite materials, microsystems, and uncertainty quantification. He is author of over 195 refereed articles and book chapters and the co-editor of 7 book volumes. And also, last not least, as you know, he's the chair of this conference, and I would like to take this opportunity to thank him very much for all the efforts he and his team has dedicated to the preparation of this conference. It has been a great pleasure to work with him, and I would like to invite you all to give a special applause for this work.
Thank you for that generous introduction, Christoph. I appreciate that very much. Can we get this slide refocused a little bit, please? Okay. All right, while they're working on it, what I want to do today is give an overview of the Sunshot Initiative of the U.S. Department of Energy. And there's a great momentum that's been set in place by the initiative across the country. And so what I hope to give you is a sprinkling of those activities, at least at a broad level. And you'll hear a lot of those presentations throughout this conference. I see a number of our awardees presenting papers in this conference, so you'll get to hear more about that, including the technical keynote this afternoon on supercritical CO2 power cycles. Right, that looks good. Okay, so what is the Sunshot Initiative? The Sunshot Initiative is really a national collaborative effort involving the industry, academia, national laboratories, policy-making organizations, and regulatory agencies to drive the cost of solar-generated electricity down to a level where it is on par with the cost of other sources of energy on the grid. And the key word is that without any subsidies, and we want to achieve that by the year 2020. So it's a pretty aggressive goal to make sure that the solar-generated electricity is competitive with other forms of energy on the grid. So the Sunshot program within the U.S. Department of Energy is organized into a number of sub-programs or teams. And there are 2 core technology areas. One is the photovoltaics, and the other is concentrating solar power. And supporting these 2 core technology areas are 2 other programs. One that's called systems integration or grid integration, and that talks about how do you take the electrons that are generated by each of these technologies and then interface them with the grid. And the 4th program or the 4th sub-program is what's called the balance of systems or soft costs, and that really deals with issues, non-hardware related costs, such as siting, permitting, and so forth. So the idea is to take a holistic view that integrates both the core technology as well as how do you take the technologies and really make it available on the grid in a manner. So the Sunshot Initiative goal is applicable to both PV as well as CSP. And the team really works together to enable this and to make this happen through a number of funding initiatives. I lead the Concentrating Solar Power Program, and I'm also leading the Systems Integration Program within the initiative. So what I'll talk about today is primarily the CSP activities. So in terms of quantitative measures, what we want to do is to take a levelized cost of energy, and here I have the 2010 basis for CSP. That's about 21 cents a kilowatt hour, and again, this is without any subsidy. And what you see there are the breakdown of this LCOE in terms of the subsystem costs, and it'll be clear what those color bars mean in a minute. But the largest bar that you see there is a solar field, and then the other ones represent the thermal energy storage, power block, and the receiver costs. So what we want to do is to take this value and drive it down to 6 cents a kilowatt hour by 2020. And how do we do that? So we've done techno-economic analysis, and we have this waterfall chart which says what are the potential cost reductions that can be achieved in each of these stacked up bars, so that when you add them up, eventually it stacks up to 6 cents a kilowatt hour. So there are cost reductions targeted in the solar field, the power block, receiver and heat transfer fluids, and of course, thermal energy storage. Okay. So this becomes kind of the guiding map for how we want to achieve the cost reduction that we set out to achieve. And of course, from a technology point of view, technology program point of view, levelized cost of energy is kind of the ultimate metric, but we want to translate that to technical targets that can be used to drive our solicitations and the programs that we fund. So if you take the 6 cents a kilowatt hour end goal, and if you use techno-economic models and kind of inverse map what the technical targets of each of your subsystems should be, so that when they integrate together, you'll get the 6 cents a kilowatt hour target. You can do that exercise, and what we have are the technical targets that correspond to this. So I'll show this and then go through this one by one. So the solar field, as I mentioned, is the largest cost of a CSP plant. So the goal there is to get the cost of a solar field down to about $75 a meter squared or less. And that's a pretty aggressive goal. If you think about current technologies, they're anywhere from $180 a meter square to upwards of $200 a meter square. So it's not an incremental change, it's a pretty significant change in the cost of the solar field. While at the same time, we want to make sure that the optical performance is high and it can survive the field in terms of the environment, the wind loads, and so forth. So those are all the constraints that drive the design and the development of the solar field. Now, the second component there is the receiver, and the goal there is primarily to go to high temperature receivers, and at the same time having about a 30-year lifetime, and with a cost target there that you see about less than $150 per kilowatt thermal. And if you go around the wheel to the power block where you generate the electricity from the thermal input, our goal is to drive the efficiencies of the power block to upwards of 50%. So 50% or more efficiency of conversion with dry cooling. So that's pretty challenging. So the best of steam Rankine cycles are somewhere in the 40s, in the low 40s. So it's about a 10% or more change in the conversion efficiency compared to that with dry cooling. The next piece around the wheel is the heat transfer fluids, and here we're targeting high temperature heat transfer fluids, again to take the heat from the receiver that's operating at high temperatures and to take it to the power block through a heat exchanger or to thermal energy storage. And the last but not the least component of a CSP plant is the thermal energy storage. And here our target is to drive the cost of the storage to less than $15 a kilowatt hour. And at the same time having a very high, what we call exergetic efficiency, so which is a combined first law and second law efficiencies. And you can read the other specs in there, but these are the principal ones. So the bottom line is that we need to go to high temperatures so that we can achieve the high efficiencies and therefore drive the costs down. And that presents a lot of interesting challenges. And we like to view the problems of CSP as not as a CSP problem. I mean, fundamentally, these are materials problems, chemistry problems, heat transfer, fluid mechanics problems. So our goal is really to bring together a diverse set of participation from various technical fields, really the bright minds across the country who have worked on similar issues in other applications, and how do we leverage those developments and then build upon those in a effective manner and an efficient manner to drive towards these objectives. So with these targets in mind, and of course once we get all these subcomponents, you can think about integrating them. That's the system integration aspect of it, but we're not there yet. I mean, I think we need to develop these subcomponents to their targets, and then we'll think about integrating them to demonstrate this final objective. But this has been a guiding book or guiding aspect of how we define our funding opportunities. And you can see a number of competitive programs. And by the way, every single dollar that goes out of the program is competitively awarded. And so you can, as I go through this, you'll see a number of solicitations that have come out since the inception of the Sunshot Initiative in 2011. And then there are a few other programs that occurred before that that have since been redirected towards the Sunshot goals. So you can see a significant number of initiatives, and more importantly, the dollar value of these initiatives are pretty significant. If you total it up in the last 2 years, these amount to about $130 million or more of investment in CSP-related technologies towards the Sunshot goal. So there's a great amount of investment towards the very challenging objective that we have set forth to do. So what I want to do today in the remaining time is to really kind of go through a very high-level overview of each of these initiatives. And maybe towards the end, I'll tell you how these initiatives come about. I mean, it's not like they're randomly pulled out of thin air. There's a lot of diligence. There's a lot of homework that goes behind putting forth each single initiative, and I'll probably have a few minutes to talk about that as well. So let's talk about some of these one by one. One of the initiatives that we launched earlier this year, or later in the later part of last year, 2012, is what's called the CSP Hybrid Initiative, which is really to hybridize or to catalyze hybridization of CSP with fossil sources. And we know that we heard in a number of presentations that CSP offers very synergistic opportunities for hybridization with fossil sources. I mean, CSP in many ways is a very enabling technologies and a very friendly technology with many other sources of energy. And one opportunity is to integrate with hybrid. And if you look at the potential for hybridization, and this comes from the Solar Prospector study, there's about 11 to 20 gigawatts of fossil plants that are potentially amenable, ready for hybridization. So our goal is that, can we catalyze the hybridization? In other words, fund a few projects to get some performance data, get some key performance metrics that can in turn elicit and elucidate the benefits of hybridization, and then therefore seed the hybridization efforts in a more greater manner. So towards this end, we put out the solicitation, which we targeted about $20 million, and we received a number of applications. Very, very interesting. We were very pleased with the turnout on that. And what we are about to do is make an award to one of the applicants, which is led by a utility company, and it's for integrating CSP, a 10 megawatt CSP with a 500 megawatt natural gas-fired combined cycle base load plant in California. And you'll see the announcement coming out in the next week or two, within the next 2 weeks, but it's very exciting. We are quite excited about that. It's a $10 million investment by DOE and a cost share of $30 million or more by the recipient organization. So watch out for the announcement on that, and that's the outcome of the hybrid for us. So we ended up making just one award, even though we planned to make more than that. So the other initiative that we launched in 2013 is solar manufacturing. Again, I keep going back to the largest slice in that LCOE bar that I showed you, which is the solar field. And one way to tame the cost of the solar field is to reduce the cost of the manufacturing assembly installation aspects of the solar field. And so again, our target here is this: can we want to get to less than $75 a meter square, that's for sure. But can we reduce the time for installation? So for example, typically a 250 megawatt plant takes about 2 years or so to put the field together. Does it need 2 years? I mean, in that time, there's a project financing, you're paying the interest on that. There's, so many costs associated with it. Can we drive it down to 6 months or less? I mean, that's a pretty aggressive target. So that requires automation. That requires, standardization of processes and so forth. So there's tremendous opportunity. And can we derive some knowledge and the insights from other industries that have gone through similar exercises in reducing costs? So that was really the goal of solar manufacturing. And this we put out as a cross-technology initiative that covers both CSP and PV. And again, we are about to make an award, hopefully in the next 1 week or two, on the solicitation with regard to CSP. The third initiative that we launched this year is what we call Predicts. I mean, you can tell that we are getting pretty creative with acronyms for some of our initiatives. So the Predicts is really what we call physics of reliability, and it's to say that, can we use the fundamental science and knowledge and understanding to predict the lifetime degradation and failure of components in a CSP plant. So in other words, all goes towards giving that assurance about the reliability and the operation, sustenance of a plant, and therefore improve bankability of the projects. Okay? So rather than doing empirical correlatory exercises, can we use the fundamental science to understand why things happen the way they happen, and in turn use that understanding to design products and processes better. So that's the objective of the opportunity. And again, this was launched as a cross initiative. This issues is common to PV, CSP, and everything else. So we just launched it as a cross office initiative. And again, we are about to make one, maybe 2 awards in this initiative. Again, all in the next 2 weeks. Another initiative that we launched and which we are going through the process of evaluating proposals is the concept of, can we store the sun's energy in terms of chemical bonds? I mean, we know that there is sensible energy storage, there's latent energy storage, but can we conduct a thermochemical reaction in the solar receiver, and then store the products of that reaction, and then in turn conduct an exothermic reaction to release the energy when needed to send to the power block. Okay, and you can see the chart here in terms of why we want to do that, because there's a tremendous opportunity in terms of the energy density of thermochemical reactions compared to sensible and other means of storage. So can we tap into that? So that's a question. So the first issue is, can we engineer a CSP, integrated thermal energy storage or energy storage, based on chemical reactions to capture and release energy on demand? And the answer is yes. I mean, we know that, right? But the question is, can we do that in a manner that meets the Sunshot objectives? I mean, that's really the key challenge. So we put out this solicitation called Elements, which is really to develop thermochemical energy storage for CSP applications that meet the Sunshot targets. And what's interesting is that you can actually look at the efficiency, the exergetic efficiency, versus the energy density of the various reactions. And you can say that if you have very high energy density, maybe you can get away with a lower exergetic efficiency, because after all, they both relate to capital cost and therefore the cost of the CSP plant. So, I mean, there's a lot of diligence, a lot of homework that goes into how we construct these targets. But this is a target. This is a set of targets that we put out. There are 2 categories of proposals that we solicited. One that are called seedlings, and the other, there are integrated systems to demonstrate the concept. So those are the 2 topics that you see on the screen there. And again, we received the proposals. We're in the process of evaluating them. I think it'll be later this calendar year that we will have some announcements on the projects that we fund in that. This was put out as a $20 million solicitation. I want to go back to some of the awards that we have made last year. I mean, all the ones that I talked about so far are the initiatives that we launched in 2013, but there are awards that we made in 2012. One of them is what we call the Sunshot CSP R&D, and this was a $56 million award set that we announced last June or July of last year. And really the awards were in 3 categories. I mean, one that addressed the issues pertaining to the collectors, and the other set of awards address issues pertaining to the receivers, and the third on developing power blocks that meet the Sunshot objectives. So you can see the sprinkling of logos that denote the recipients in each of those categories. But I just want to quickly go through some of them, in a brief manner, so that you get an idea of the spectrum of activities that we're funding. So in the area of collectors, 3M and JPL are developing advanced collectors. Both 3M is looking at polymeric films in collaboration with Gossamer, who will provide the structural support to see, can we develop low-cost structures that meet the Sunshot objectives. JPL, you'll recognize, is a NASA laboratory. So again, this goes in the spirit of we are broadening the reach to beyond what's traditionally considered a CSP community to anybody who has the right ideas and the right technologies to solve the problems that benefit CSP. And we believe that's the right way to advance the technologies in a manner in the short time frame that we have to achieve our goal. So JPL is bringing their expertise from their satellites and other applications that they are familiar with to see can they devise collector structures that will be applicable to the CSP targets. Boston University is looking at self-cleaning collectors. And the University of Arizona and BrightSource are really solar manufacturing projects. Can we reduce the time of manufacturing and the costs of manufacturing? And Penn State is actually looking at non-imaging optics. I mean, do we need to have imaging optics as a way to collect the sun's energy? Can there be other ways to do that? So Penn State is looking at options in that regard. In terms of receivers, we have a couple of projects on supercritical CO2 receivers. Oregon State is looking at one of those, and Brayton Energy is looking at another. There are two projects on falling particle receivers, and I think there were presentations on both of those at this conference, one led by Sandia National Labs and the other led by NREL. And Norwich Technologies is looking at new high-temperature receivers for linear systems, parabolic trough systems. And San Diego State is looking at particulate receivers that are based on generating soot particles so that absorb the energy and then generate high-temperature air for air-braking systems. Now, in terms of power cycles, we have two projects that are on solid-state power conversion, one by MIT on thermoelectrics with integrated thermal energy storage, and the other by Stanford that's looking at thermionics. So for a topping cycle that will then bottom out with either supercritical CO2 or some other cycles. And then we have two projects on supercritical CO2 at a very significant scale, one led by Southwest Research Institute that's developing the cycles and especially the turbo machinery components for a 1 megawatt demonstration, and that's in partnership with GE. And NREL is leading another project at a 10 megawatt scale, again in partnership with industrial collaborators. And Pacific Northwest Lab is actually looking at hybridization. So it's essentially to use solar energy to boost the value of of natural gas for hybrid configuration. So it's a pretty exciting lineup of projects that we funded through this, and they're all in their initial stages still, so we'll see the fruits of those in the next year or two. But again, the spectrum of activities is really exciting. Now, we have the heat transfer fluids projects that we set out to solve using a collaborative university initiative called Multidisciplinary University Research Initiative. Here we have two teams of universities, one led by UCLA with partners from Berkeley and Yale, and they're looking at developing high-temperature liquid metals for solving the heat transfer targets that we have for the Sunshot objective. And the other team is led by the University of Arizona with partners from Georgia Tech and Arizona State, and they're looking at molten salts to work at high temperatures. And both these projects are going well, and they're again in their initial phases. But the nice thing is that all of these are set towards the objective. So even though it's a university project, their goals and their deliverables are in an applied context. So we really approach this like a puzzle piece. So all of these different awardees are working on the different pieces of the puzzle, and we give the boundary conditions on how they interface with the other components of it, so that when the technologies are ready, it's more or less a drop-in replacement to the current technologies. The national laboratories are an integral part of our portfolio. We fund the industries and the universities, as you've seen before, and the national laboratory is another part of it. And the national laboratories have two mechanisms to compete and get money. One is through the funding opportunities that we put out. I mean, they are open to compete in those solicitations, but we also periodically put out solicitations that are open only to the national labs. And we did one of those last year, and these are usually 3-year cycles, so the next one will be in the next year or two. But essentially, we had a number of projects from the various DOE national labs, and out of those, there were 12 projects that were picked. NREL has 4 projects, and I'm not going to go into the details of those, and Sandia has 3. We are engaging Savannah River National Labs on 2 projects. One is looking at metal hydride-based thermochemical energy storage systems, and the other one is looking at corrosion aspects of molten salts with containment materials. Los Alamos is looking at a heat pipe-based receiver for power tower applications. And Oak Ridge National Lab has a very interesting project on self-cleaning collectors using super hydrophobic coatings without any loss in the optical properties of the collectors. And Argonne is looking at thermal energy storage based on PCM with metal foams. I want to mention a couple of cross-program initiatives. One is called the Bridge, and as you know, the Office of Science of the Department of Energy has a number of user facilities that have been built over time. They're pretty fantastic facilities. I mean, there are computational facilities, characterization facilities, and so forth. And again, in our quest to achieve this applied objective with the fundamental science understanding, that's the driving force behind the applied development, why don't we leverage the vast infrastructure that exists in the Office of Science? So the Bridge program is really, is an acronym, but it's really a bridge between the applied and the fundamental science aspects of DOE. And we put out a solicitation, and one of those is in CSP. One of the awards is in CSP that's looking at the computational facilities that are available at Oak Ridge, and to use them for very high fidelity simulations pertaining to falling particle receiver development. So it's a complementary to the projects that we have on falling particle receiver development. The other very successful program of the Sunshot Initiative is the incubator program, which is really a program that's designed to bridge the valley of death, as it's called, between when you come to a technology prototype at the end of an R&D project, and before you go to a venture capitalist to receive other sources of funding, private sources of funding. So how do you bridge that gap? And so the incubator program is really designed to bridge that gap. And it's a yearly solicitation, and it particularly targets smaller companies. And it's been a very successful program. And again, it's across technologies, not just CSP, but a couple of awards in those are in the CSP area. One to Halo Techniques, the other to SolarFlect. Halo Techniques is looking at developing storage, and SolarFlect is looking at novel collectors. And the success of the program is shown there. I mean, about $90 million worth of DOE investment has eventually gone on to leverage close to $2 billion of private investment. And that's a measure of the success of the federal funding, and how that leads to applied development. I'm not going to go through this in detail. There are a number of programs that we put out before Sunshot, and they're still, some of them are still part of our portfolio now. But really, I mean, they started before Sunshot, but then towards the end of their projects, they were redirected towards Sunshot. But they still led to some developments that were the foundations and the stepping stones to the refinements that or the developments that we're doing as part of the Sunshot objectives. I also want to mention that we work closely with our sister organization, ARPA-E, on some of the programs. I mean, ARPA-E has a broader mission. They look at energy in general, whereas ours is a very applied mission, particular to solar. But again, we use the same targets in some of the solicitation. The ARPA-E HEATS, which was on thermal energy storage, use the same targets that I mentioned for storage. The ARPA-E Open FOA, which is really a broad call for proposals in anything, everything but the kitchen sink, is again using some of the targets that we put out. And there are a couple of solicitations on the street right now. I think there's a solicitation called Focus, again looking at some of these CSP aspects of it. So there's a variety of opportunities to get involved in CSP through any of these funding mechanisms. Now I want to talk a little bit about how this competitive funding process happens. I know I'm running a little bit over time, but let me know.
2-3 minutes.
Okay. 2-3 minutes? Okay. All right. So how does solicitation really happen? So there's a lot of effort that goes on before you see a solicitation announced in a public forum. There's at least a 4 to 6 month period of incubation of ideas. So it starts with a vision. I mean, what do we want to do next? What's the next thing that we want to achieve? And there's a constant effort of doing the research, talking to the stakeholders, getting information, and really seeing what are the targets that we need to set, more or less stretch targets that we need to achieve. And that happens all the time. That's happening now. I mean, so it's a very intellectually stimulating team that I have that's constantly debating and creating ideas. So once we go through the research and discussion, vet those ideas, and we say, okay, it makes sense, then we say, let's calibrate it. Let's put a workshop and get folks from the outside, and to really say, are we on the right track? I mean, does this make sense? Is this even worth federal funding? And there are many times where, some solicitations that we thought were nice. I mean, we realized after the workshop that this is, the stakeholders told us that, this is not worth federal funding. This is something that the industry would do on its own, or whatever the case may be. So after we go through that vetting process, and after it's still a go in terms of proceeding with the idea, then we decide what the budget for that solicitation should be, and we write it into our budget request to Congress for a future year. So once we have that funding, and then we release the funding opportunity announcement, what's called FOA. And the FOA process is that we typically have a concept paper or a preliminary application that basically says, what's the landscape of applications that we may get. We may give feedback on that, to the applicants if we invite them for a full proposal. And once we get the full proposal, then essentially then it goes through a merit review process. We can convene experts in the field, and these are pretty distinguished members of the community. Again, like I said, not necessarily CSP. These are people who work in high temperature materials and so forth, and many of them are members of the National Academy of Engineering, National Academy of Sciences. It's a pretty high profile merit review panel that reviews this and makes recommendations to us. So out of the shortlisted applicants, we actually do pre-selection clarification. So we'll actually bring those applicants to DOE for a presentation, for discussion, or we may go to their site and have the same discussion with them to get clarification on that application. It's more than just what's on paper. We actually try to understand what's being proposed, in the shortlisted set of applications. Once we go through that, then basically we negotiate the award once it goes to the award stage, and the program managers who work in the team are very actively engaged in each of those. Again, we are vested in it right from the beginning. Right from the vision creation stage to the application selection stage. So we set out the objectives that each of the projects should achieve, and then it leads to an award. Once an award is made, again, we're not hands-off. The team stays engaged with each and every project of it through periodic technical monitoring, and it's pretty rigorous technical monitoring. It's not just a government report per se, but it's really delving into the technical details of understanding what each project is setting forth to do. And the program managers are often one up on the awardee in terms of guiding them, directing them, asking them critical questions, and guiding the thought process. So we go through that, and then at the end of each year, we have what's called the go, no-go decision relative to the quantitative milestones that we set forth for each project to achieve. And then if it's a go, then it goes to the next phase, and then once it clears all the go, no-goes for each of the phases of the project, then it leads to a successful completion of the project. So it's a pretty very interesting process, a very engaging process, and a very rewarding process in terms of how each single federal dollar is leveraged to achieve the applied objective that we set forth to do. Again, this is just a pie chart on where our money goes. Again, like I said, we fund the industry, universities, and the national labs, and we are technology agnostic. We fund all technologies. And I want to close with 1 or 2 slides on just the commercial deployment. And the loan guarantee program of the DOE has funded 5 commercial projects, and that are in various phases of completion towards starting to work. And the earliest one, I think, is Solana, that will start delivering electrons maybe this month or next month, and following the the heels of that plant, would be the Bright Source and the Genesis project and Crescent Dunes, and also the Mojave project later this year. So you can see the status of the various projects as you see in that chart. But the point is that when these projects are completed, we'll have about an extra 1.3 gigawatts of CSP generated electricity on the grid. And in March of this year, a collaborative effort by Abengoa and BrightSource announced the Palin project. And if that project goes through, then that's an additional 500 megawatts of CSP generated capacity. So there is some significant activity that's going on in terms of putting CSP on the map. And then once these plants get going, I think there'll be a lot more information that's gained, a lot more public appreciation of CSP, and we are hopeful that that'll be the starting point for more things to happen, along with the developments on the research and development side through the Sunshot Initiative. So again, this is a chart of how it stacks up in the global landscape, and again, it's just reiterating what I just said. But the interesting thing is that the rest of the world chart, the bar there is currently small, but I think it'll be interesting to watch that bar grow over the next few years as to how it stacks up to the rest. And I think it's overall an exciting time for CSP. Again, thank you very much, and I appreciate your patience through this extra time through the presentation. I guess as a chair, I have the prerogative to override the time limitation. Thank you very much. I appreciate it. I'll be happy to answer any questions, and again, I'm available throughout the conference if you want to take it offline as well.
And we have time for a few questions now, I think. Okay. So, please come to the microphones and ask your questions.
Mark, it's okay. Mark Ben Maraz, Solar Euromed. Thank you, Ranga, for this tremendous presentation, this vision, and this fantastic implementation program. My question is related to, I have seen that the program addresses the electrical, the conversion, solar to electricity, the hybridization, and my question is related to all other use of CSP, in particular process heat. Is there any, let's say, inside this program, allocation to process heat applications, or maybe additional programs?
Yeah, that's a good question. I mean, there are clearly other applications of CSP than just power generation. But by mandate, our program is restricted to funding those efforts that lead to electrons on the grid. So, it's not within the purview of our program or the Sunshot Initiative to fund other activities such as, enhanced oil recovery or desalination and those types of projects. But there may be some opportunities in other parts of DOE. Maybe there is some opportunity in the buildings program to do some other solar thermal applications related to those types of end applications. Again, within the context of the scope of each of those particular programs. So right now the focus is mostly